This video is going to go through a few examples of using double angle formulas in proofs. So the first example, we're looking to prove that the sine of the double angle theta is equal to 2 tangent plus 1 over tangent squared. So I'm going to look at the right-hand side to evaluate, and I'm going to leave 2 tangent theta at the moment because I can identify that 1 plus sine tangent squared, is secant squared of theta. And as we've done before, we're now going to change tangent to sine over cosine and divide this by 1 over cosine squared theta. The algebra to follow shows that sine and cosine times 2 will get multiplied by cosine squared theta. Algebraically, we can eliminate cosine squared down to a cosine and this cosine, which now ultimately gives us what we are looking for to be 2 sine theta cosine theta. This is equal to 2 sine 2 theta. This is our identity. So we have sine 2 theta, and that is what we want on the left-hand side as well. So sine 2 theta is equal to sine 2 theta. And we've done a proof with a double angle formula. The second example is a little bit more involved algebraically. You're looking to see that the tangent plus the cotangent is equal to 2 times the cosecant double angle. Using the cosecant double angle formula, which is equivalent to 1 over the sine of our double angle, we are going to write out and expand sine of our double angle as 2 sine of x cosine of x now in the denominator. Algebraically, our 2's will cancel out to become 1, and we have 1 over sine x cosine x. Similar to proofs we have done in the past, we are going to look to change this 1 to be in terms of sine and cosine. We know 1 is equal to sine squared x plus cosine squared x. And we're going to leave that over sine x cosine x. When we split each of these values in the numerator up, so we have sine squared x over sine x cosine x plus cosine squared x over sine x times cosine x, we can see that individually each fraction can be reduced. In the first fraction, we can see that a sine and a sine will cancel, and the second fraction, cosine and cosine will cancel, giving us 2 new fractions of sine over cosine, sine x over cosine x, plus cosine x over sine of x. These 2 fraction ratios we know in terms of tangent and cotangent. And that is what we wanted to begin with, tangent x plus cotangent x. And we're done. So the trickiest part here is then in this step here, where we want to take this 1 and rewrite it as sine squared plus cosine squared. Okay, example 3. We now have something slightly different than we've seen before. We actually have sine of a 4th angle, okay, not a double angle. But what we know about a 4th angle is that it is twice a double angle. So in this particular problem, we're going to rewrite the left-hand side as the sine of 2 double angles. So that means the sine of the double angle of 2x. This is now our angle, right? So this sine expansion is 2 sine of our angle, which is 2x, cosine of our angle, which is 2x. we rearrange some of these terms. Not rearrange, I apologize. We rewrite sine of 2x, double angle, we expand that out again. We now have 2 times 2 sine x cosine x times cosine of 2x. This expansion then, now if we multiply, we have 4 cosine 2x. We rearrange because multiplying, order doesn't matter. And then we're going to multiply by sine x, multiply by cosine x. And that is exactly what we want on the other side. So a slightly different step in this one for transitioning the sine of 4x. It is twice the angle of 2x. Right, so we're expanding out sine of 2x, and then within that, expanding out sine of 2x again. Our final example using double angles is now cosine squared of the double angle plus 4 sine squared times cosine squared, and that is equaling 1. How do we do that? Well, we know that cosine squared plus sine squared is equal to 1. Can we manipulate this to get that? And the answer to that is yes. We're looking at not rewriting cosine 2x at the moment. Looking at 4 sine squared cosine squared. Unsquaring sine and cosine, we have 2 times sine x cosine x times another 2 sine x cosine x. So breaking up that product of 4 sine squared cosine squared to 2 different 2 sine x cosine x. Well, each of these 2 sine x cosine x, each of those are a separate sine double angle expression. And we're going to leave cosine squared of 2x. These now multiplying sine of a double angle times another sine of that double angle, that becomes sine squared of that double angle. And we have cosine squared of that double angle. And here's our identity where the square of a cosine of a particular angle, sine squared of that same angle, that is equal to 1. So 1 now equals 1, and we're done. Okay, so with the double angle formulas, you do need to be a little bit more creative, find more algebraic ways to express the same things, and you will ultimately get to the final end of the proof.